In order to explain the behavior of gases, scientists have devised what is known as the kinetic molecular theory of gases. Let's go over the points within this theory. Number one, gases are made up of small atoms or molecules that are in constant random motion and linear motion. What's important to note here is that the molecules or atoms are in random and linear motion, and they do so constantly. While in a solid, the particles are stuck in one place, and in a liquid, they move past one another, they slip past one another. But in the case of gases, they are in constant random motion. They are moving randomly and they are moving in straight lines. So if you could see the gas inside a balloon, it's made up of many tiny particles and each one is moving in straight line, and it's moving randomly. There is no such thing as all the particles moving in one direction, but they are moving in any direction in straight lines. Now the distance of separation is very large compared to the size of the individual atoms or molecules. You may think that the gas particles moving randomly in straight lines may collide into each other, but the distance is so large compared to the size of the individual particles that they don't necessarily run into each other. A gas is mostly empty space. You could take that balloon and you can squeeze the particles, compress the particles of gases, and create a very tiny amount of volume in which you can have all those gas particles. All gas particles behave independently. This is very important. They are not attracted or repulsed by each other when they come into close contact with each other, with each other. Now just remember that the kinetic molecular theory of gases defines the behavior of an ideal gas. A real gas will deviate slightly from what the kinetic molecular theory of gases states, especially point number 3, that there is some attraction or repulsion between gas particles in a real gas. And the last point, gas particles collide with each other and with the walls of the container without losing energy. If two cars collided with each other, they would lose the energy in many ways, to friction, to heat, and to absorbance by the material of the car, and so on. But when gas particles collide, that collision is said to be an elastic collision, meaning that the energy is not lost at all. When they collide, they bounce back, and they bounce back at the same speed, moving in the opposite direction now, but not without losing any energy. They don't lose any energy at all. The energy is transferred from one atom or molecule to another, but the overall energy is kept the same. And actually, there is one more point: the average kinetic energy of the atoms or molecules increases or decreases in proportion to absolute temperature. If we increase the temperature in a gas, the kinetic energy, which is the speed of the particles at which they are moving, will become faster. And there is an average kinetic energy, meaning that there are particles with slow speed, then there are particles with high speed, but then we can average all those speeds up, and when we raise the temperature, we are raising the average kinetic energy of the gas molecule. And so these are the 5 points of the kinetic molecular theory by which we define how an ideal gas behaves. Because of the kinetic molecular theory, we can say gases are easily compressible because they are mostly empty space, and they will expand to fill any available volume, since they are mostly empty space, and they can always add more empty space to their volume. They readily diffuse through each other as they are in continuous motion and paths are readily available. Gas molecules, even if they run into each other, they behave independent of each other due to large space between adjacent particles, and they keep on moving. Gases have low density because of lots of space in their midst, empty space. They exert pressure on their containers. How exactly do they exert pressure on their containers? Well, when the gas molecules collide with the walls of the containers, the collisions are perfectly elastic. The gas molecules do not lose energy, and that's how a balloon remains stretched, because the gas molecules moving at very high speed are randomly colliding with the walls of that balloon. Gases behave most ideally at low pressure and high temperature. So real gases are gases which will deviate from ideal behavior at high pressure and low temperature. When the temperature is very low, the particles will come very close to together, and that's when they will start interacting with each other. As a matter of fact, if real gases did not behave like that, if they did not deviate from ideality, there is no way to condense a gas into a liquid, because when the temperature goes low and the particles, the average speed of the particle goes down, they come close towards each other and they are attracted to each other, condensing from gas to a liquid. So we want that deviation from ideality at very low pressure. And at very high temperature, rapid motion overcomes interactive forces more easily. So they behave most ideally at high temperature. But at low temperature, they will not be able to interact, not be able to overcome that attraction. At high pressure also, they are forced to come very close, and they will then be attracted to one another. So here is an example of two gases. One is hydrogen chloride gas on the left and ammonia on the right at the start of the experiment. Both of the gases start moving in the space provided to them, and they start diffusing, and they move in whatever space is provided to them in random direction, which for the case of hydrogen chloride it will be to the right, and for ammonia it will be to the left, because they are highly concentrated in their original region where they start off. Now when they meet, they form ammonium chloride, which is a solid, and that happens right here. You might say, why not at the center? Because it turns out that the speed of diffusion of gases depends on the size of the atoms or molecules involved. Hydrogen chloride, because of chlorine, is a much heavier gas. 36.5 grams per mole is the molar mass of that gas, compared to ammonia, which is 17.0 grams per mole. So ammonia is able to move faster, and while hydrogen chloride has barely started moving, ammonia catches up, and that's where the reaction between them happens here.